The name of this video is Coulomb's Theorem. This is one of the most important results for conductors in macroscopic electrostatic equilibrium. While it is called Coulomb's theorem, has nothing to do with Coulomb's law, although everything we have done up until now, that is Maxwell's equations for the electrostatic field, are of course derived from Coulomb's law and the superposition principle. And in fact, Coulomb's theorem is nothing but a special case of a Maxwell equation for the electrostatic field, case 2. So let us consider a homogeneous that is made from the same material, for example, a block of copper, conducting material, which is also isotherm at some thermodynamic temperature, capital T, in normal conditions. Okay, with all this hypothesis, let's hypothesize that the volume of this object is capital omega. The surface of this conductive object is, as always, capital sigma. This can be charged or uncharged. We'll discuss about this in a few minutes. This object is assumed to be in macroscopic electrostatic equilibrium, MEE, macroscopic electrostatic equilibrium. A consequence of macroscopic electrostatic equilibrium, as we have seen in the previous video, is that for each point, capital P, within the volume, the bulk of the object, capital omega, the electrostatic field, the total electrostatic field E, at such points, capital P, has to be identically equal to 0. Again, even if there is an external electrostatic field, if we wait long enough, that is much longer than a typical transient time of femtoseconds, this is what happens in macroscopic electrostatic equilibrium. E is equal to 0 within the object. We also know a fundamental law of the electrostatic field, which is Maxwell's equation, case 1, the differential case, for Gauss's theorem. So we know that according to this law, the divergence of E is equal to rho divided by epsilon naught. As a consequence of the macroscopic electrostatic equilibrium condition, since E is equal to 0 at each point in the bulk, this also means, and again, we have bulk here and vacuum outside, so this is in vacuum outside, bulk inside. Obviously, from this, it has to happen that at each point, capital P in the bulk, capital omega, it has to be the rho at such points, capital P, has to be identical equal to 0. This is an important result. So in macroscopic electrostatic equilibrium, MEE, rho is equal to 0 within the object, which again tells us that qualitatively we can consider a conducting object in MEE, in equilibrium, by replacing it as only the container which contains the object, that is the surface capital sigma. We don't care whatever is going on within the object. Of course, there is an Avogadro number of ions, an Avogadro number of electrons, a Fermi sea of electrons moving around, but we only are interested in what happens on the surface, not what happens in the bulk. This is the key essence of Coulomb's theorem. Now that we know this, and again, we can only consider the surface, the boundary of this object, this really resembles a situation of nothing, something on the surface, nothing. And this is nothing but case 2 of Maxwell's equations in local form for the electrostatic field. Why this is a special case of case 2? It is a special case of case 2 Because in this specific case, the electrostatic field within the object is identically equal to 0. So let us write down the case 2 in general. Remember that it's a local form, so eventually we need to consider a limit operation, but for now, let's write it as follows. First of all, let's pick a point on the surface capital sigma. Let's choose a point here. This is a point capital Q, since there will be a local charge density, which is the one which nullifies the electrostatic field within the object. This point, we will call it capital Q as a source point. Around this point, we can consider an infinitesimal neighborhood with area dA. And as always, so this point is point capital Q on capital sigma. All right, so now we can consider a normal unit vector, which always points outside the conductor, is a convention. This is n, the normal unit vector at capital Q, pointing outside. So this infinitesimal area element is oriented, and we call it MdA. To map it to case 2 of Maxwell's equations local form, we want to define the region within the object as region 2, for example. You can do the opposite. So within the object in the bulk is region 2, and outside in the vacuum, region 1. Remember that n has to point from 2 to 1. That's why we're choosing pointing outward, and that's why we've chosen 2, 1. So in this case, as soon as you choose n pointing outward, you should really follow our convention 2, 1, 2, 1. And if you can invert it, then you need to invert all the equations. So let's keep it 2 to 1 for consistency. So we write actually here n to 1, and let's write it also here for completeness. Okay, great. So this is my infinitesimal area element oriented according to n to 1 from region 2 to region 1, which is vacuum. So we will have an electrostatic field E2 inside, E1 outside. So let us write down this case then. So here we can write down n to 1 dotted with, so we are projecting E, which was E1 minus E2. We are projecting along n to 1. This, in this specific case, becomes simpler because E2 is within the bulk, is in region 2. In region 2, he has to be equal to 0. So this quantity here is identically equal to 0. Since we end up having only one E with one subscript, it is custom to remove this subscript for simplicity, therefore obtaining the projection of E outside, projected along n to 1. This quantity, which is nothing but the normal component for simplicity, let's just call it En of the electrostatic field slightly outside, has to be equal, case 2, is nothing but a special case of Gauss's theorem. Small sigma is any surface charge density with distribution of small sigma on capital sigma, and this can be varying with point capital Q on the surface capital sigma. For example, I remind you that if this object was immersed in an external electrostatic field generated by some other sources, this, the fact that there is an external field, as soon as I switch it on, the charge-free carriers, the electrons on the conducting object, start to migrate following the field lines, of course in the opposite direction of the field lines. We have seen this cartoonish representation of a conducting object in a previous video. So now, what happens is that these charges start to redistribute on the external surface capital sigma in such a way that the reaction field within the object is equal and opposite to the external field, so that again, E inside the object is identically equal to 0. So there will be effectively a specific sigma which always nullifies the field inside. This we call it sigma and capital Q, and I remind you that this is a local property. So it's a local definition of sigma. It varies point by point. Typically, people make mistakes here because they say, oh, but the object was uncharged. Well, when we will integrate over the entire surface, yet you need to obtain a 0 overall result. But locally, it doesn't have to be. Okay, so remember, for example, in the infinite slab, we had an effective accumulation of negative charges on the left, positive on the right, but the sum was still 0, so it remains uncharged. Sum is integral, so this divided by epsilon naught. This is nothing but a special case of case 2. Okay, so we get EM is equal to sigma q over epsilon naught. Typically, we want to further improve this definition here, well, this result, because again, we really want the essence of case 2 is in a neighborhood around each point on the surface of capital sigma. So we want to introduce, actually must introduce, a limit, because of course, if we start to consider the field here, we can use the differential form. In fact, we can use Laplace equation. So let's really go to a neighborhood around a point on the surface. How do we go to a neighborhood? With a limit. So this, more properly, we write as the limit. For what point? Well, let's consider a point on this axis here. For example, in this example, capital P, which is anywhere outside in region 1, which approaches this point, capital Q, from the outside. So we want to perform the limit for capital P that approaches capital Q from the outside. We say this to be Q plus, because we are approaching from outside. The limit of En estimated, evaluated upon capital P, which in the limit becomes Q plus, this has to be equal to, on the right-hand side, we are right on the surface. You see, this is kind of critical. On region 1, we are in the limit. So we are not considering the field right on the surface. We are approaching it. So we are in the vacuum approaching the surface. Whereas for sigma, this sigma only lives on the surface itself. So there's no limit on the right-hand side, which reads again, sigma, small sigma, capital Q divided by epsilon naught. Okay. So this is the first part of Coulomb's theorem in local form, which again is a special case of case 2 of Maxwell's equation for the electrostatic field. So it's a special case of Gauss's theorem. Now let me introduce, before looking at the second part in local form, a few definitions which are worth introducing here. So typically, we define a super surface, capital sigma tilde, which we already defined, for example, when we have proven Gauss's theorem. So we call this capital sigma tilde. Eventually, for example, in the limit that the point on this surface reaches the surface capital sigma in the limit for each point on this capital sigma tilde, if we do the limit for everywhere, of course, eventually, this capital sigma tilde eventually becomes nothing but capital sigma. Okay, so this one has to be larger. It has to include, in general, capital sigma, and in the limit case, it coincides with it, so it's outside, similar to what we've done in the proof of Gauss's theorem. Most importantly, when we go in the limit to approach capital sigma, eventually we define a special type of surface, which is the one dashed here. You go all around, okay, around capital sigma, and the distance, this distance here, is dl, infinitesimal everywhere, from capital sigma. This dashed surface, we call it capital sigma plus. The reason why we use this capital sigma plus, which means is approaching capital sigma from the outside in the limit, is for simplicity, to simplify the notation in a few questions from now. So these are our typical definitions. Now let's continue with the second part of Coulomb's theorem. What is the second part of Coulomb's theorem? Well, we need to use the second part of case 2, which is the rotational property, that tells us that the projection along T to 1 of E1 minus E2 has to be equal to 0, continuity of the tangent components of the electrostatic field. Okay? So this eventually, since again the field E2 is equal to 0, E1, we can forget about this index. And so this is the projection along the t-axis. This can be rewritten as in the limit again, because we need to approach a neighborhood around the surface capital sigma, for capital P, which is outside, reaching a point capital Q from the outside, plus of the tangent component, in this case, T, a point capital P, has to be equal to 0. So this is the second part of Coulomb's theorem. So Coulomb's theorem is nothing but these two laws together. One, and 2. This is what we call Coulomb's theorem. All right. Actually, this second part implies something important, which I want you to think about in Piazza. So in Piazza, I want that you think, what is the work, if you want, work necessary to move a particle Q naught, with charge Q naught, on the surface capital sigma of the conductor? What is the work? And the result is related to this concept, a concept we already discussed previously when we discussed about electrostatic potential basics, in fact. Okay, so now we have the local form with these limits of Coulomb's theorem. From the local form, eventually, we want to find now the integral form. Not only we want to find the integral form, which we shed light on the concept of being charged or uncharged. Also, we want to use the concept of electrostatic potential. So these are the next 3 steps we are about to do. So this is the summary of the local form of Coulomb's theorem with these limits, again, approaching the surface capital sigma from the outside. Now, in order to obtain the integral form, obviously we need to integrate. And here you just need to be careful about the notation which I'm about to introduce, which is a simplified notation. People have usually problems with that, so let's try to be careful to understand what I'm doing. So in general, if we take the first case, here we want to write down the limit for capital P, which goes to capital Q from the outside, instead of the normal components of E, of the integral on the entire surface, capital sigma tilde, where point P resides on, in the limit approaching, of course, capital sigma, of the normal component. Let's rewrite it one more time for a reason which will become apparent in a minute, as the projection of E along n, n of course is n to 1, let me just call it n for simplicity. This has to be integrated over dA, because it's an area, and this has to be equal to 1 over epsilon naught, which is a constant of integration. Now here we don't need the limit, so we just want to find the total charge on capital sigma, which is the surface of the conductor, of small sigma q dA. Now here we can have a couple of different scenarios. So when we sum up this charge, if the object, the conducting object, was initially uncharged, it remains uncharged at all times. And so in this case, this quantity is equal to 0. Whereas if it was charged, so if we apply somehow a charge to it, then this result has to be some charge Q divided by epsilon naught. Okay, Q divided by epsilon naught, where Q is the total charge on the conductor. Okay, now that we understand that, the simplified form of this integral form is written as follows. Instead of writing the limit for p that goes to q plus on sigma tilde, etc., we simply write this limit as the integral on a limiting surface, sigma, capital sigma plus. So capital sigma plus encodes the concept of limit. So instead of taking capital sigma sigma and approaching capital sigma, we just say that this approaching limit is this limiting surface, capital sigma plus. This is key, because again, we are not evaluating this integral right on the surface, but a little bit outside. That's critical. Okay? Many people do lots of mistakes for that, particularly when we will introduce the concept of capacitance. Okay, so you need to be a little bit outside, not on the surface. Okay? All right, of this quantity, which is nothing but the normal component of E projected along n dA, and this is equal to Q divided by epsilon naught in general, which again, I write it in the general case, it could be 0 if it was uncharged. Even in the case that this result of the integral is 0, sigma is not 0 locally. It can be different than 0. It's just the integral could be 0 if the object was uncharged. The second law, we can write it here. Obviously, it just tells us that the integral on this limiting surface, capital sigma plus, of the tangent components of t has to be equal to 0. We just integrated it. All right, so this is the integral form using the electrostatic field, and also explains a little bit better the concept of being charged or uncharged in integral form and locally, small sigma. Lastly, we know that E is a conservative field, so we can write it as the minus gradient of V. So if we use this definition of minus gradient of V, let us focus on this equation here only, because that's really the most important one. This you typically do not use it in problems, whereas in problems we always use this one. But typically you want to deal with a scalar instead of, so you want to solve a partial differential equation, which in our example is going to be a simple ordinary differential equation, OD. We will see 3 cases of these ODs, very simple. But anyway, you want to solve this with boundary conditions using scalar functions, because they're much easier. That's why we introduced V. So if we refine this, rewrite it as a function of V, well then, remember that E is equal to minus gradient of V at point capital P. Okay, so we need to remember this minus sign, so we need to bring out a minus sign, perform the integral on the limiting surface, which again, it means simply we are doing the limit of the integral, capital sigma plus. Then we are projecting the gradient of V at point capital P, which with the minus sign is E, on the normal direction n, dA. This is nothing but a directional derivative, okay? So we can rewrite it as concept directional derivative, the integral, again on the limiting surface, so in the limit, sigma plus, of the partial with respect to the direction n, and in the problems this direction, for example, for a sphere, will be the radial direction, as we shall see soon, of V of P. So this is the result of the projection, is a scalar, dA. This quantity has to be equal in general. Let's write it more formally. Instead of writing Q, let's write really the integral on right on the surface, not in the limit of sigma capital Q. So this is the most useful form of Coulomb's theorem, the one really everybody uses in the so-called Dirichlet problem, which we are about to introduce, that is to solve partial differential equations with boundary conditions. This is one of the conditions you want to use. It's absolutely critical to use this to solve problems using the electrostatic potential and Laplace equation, as we shall see soon. Okay? So, to recap this video, we started with a homogeneous isotherm in normal conditions conducting object, like a piece of copper, with surface capital sigma, could be charged or uncharged, and volume bulk capital omega. In macroscopic electrostatic equilibrium, the field, the electrostatic field at each point within the bulk, not on the surface, in the bulk is identically equal to 0. Therefore, from Gauss's theorem in differential form, the raw charge distribution in the volume has to be also equal to 0. So we are in a special case of local form of Maxwell's equations for E, case 2, where we have nothing, the region within, not charge, a surface charge, and nothing, so case 2. But the case is even more special because the field inside is 0, so it simplifies and we obtain these two limiting equations in any neighborhood of any point capital Q and capital sigma, okay? Local form. We integrate these forms with this simplification of notation using a limiting surface, which encodes the concept of limit, only on the left-hand side. On the right-hand side, we integrate the charge distribution right on the surface. This is the integral form for Coulomb's theorem using E. We can also rewrite it using the definition of E equal minus gradient of V, so the concept of electrostatic potential. Obtaining this directional derivative, this is the most useful version. And here, the confusion that people usually do is, okay, this integral, of course, if the object was uncharged, is 0, but locally, sigma is not 0. In general, if I charge on top of everything, I put an extra charge on this object, this is actually different than 0, even in integral form. Last caveat on this, if I put an extra charge on it, we will come back to this concept later when we will study electrostatic shields. If I put a charge on this object, what happens? What happens to the field? Of course, everything is already built in here, but I want you to think, in Piazza, what happens when there is actually a charge Q on the object. So what happens when there is a charge Q? Please think about that in Piazza. And this is it for Coulomb's theorem.